right, welcome back. Today we are going to take another look at polar coordinates. In particular, we're going to talk about how we can use polar coordinates and the ideas of calculus to calculate area of under polar functions. So first, what we want to do is look at what that means. So here I've graphed the function r equals 1 plus 2 cosine theta using polar coordinates. So that means for any angle that you give me, like following this line here, this angle here, if we plug that into this function, it tells us how far away from the origin we are. So for example, what angle is that? That must be pi over 12, because then this is pi over 12, so then 2 of those makes pi over 6, and 3 of those makes pi over 4. So what I've shaded here is the region. The way to think of this is one of the things that's tricky about polar functions and area, is we're not going to think of this area as going from a curve down to the x-axis anymore. What we want to do is we want to think of this area as being swept out and going from the curve to the origin. Okay, so that's what we're going to dive into. So I wanted to zoom in on this thing a little bit. So like I said, when we talk about this area, the way we usually do it with rectangular or Cartesian functions is we use a rectangle. The problem is that with polar coordinates, the function we have doesn't tell us the height from the x-axis anymore, right? It tells us the distance from the origin. So we're going to need to use a different shape to be able to talk about area. And it turns out that the most useful shape to use will be sectors of a circle, since we are talking about the distance from the origin when we talk about polar functions. So that's going to be our fundamental shape. So in the same way that we built integrals of Cartesian functions using rectangles as kind of our base idea, we're going to do the same thing with sectors of a circle. So in order to do that, we need to know how to calculate the area of a sector of a circle. So here you can see when we talk about a full circle, that we know has a radian measure 2 pi, and we know, hopefully you remember from geometry, that the area of a circle is pi r squared. So hopefully it stands to reason that if we have only half of a circle, right, so that means the radian measure of that angle is pi, well, we've just halved the area. So what I'd like you to do is pause the video and take a couple of minutes and fill out the rest of this table and see if you can come up with an equation for the area where somebody tells you what the angle measure in radians is, and you can tell them what the area of the sector of a circle is that has that radian measure. So when we talk about a radian measure in a circle, what we mean is if you draw a circle and somebody says, hey, this angle here is theta, then we want to know what's the area of that region in the circle. Okay, so go ahead and pause the video and see if you can fill out the rest of this table and find a pattern. So if we look at this, certainly when we cut a half in half again, we get a quarter. And so, oh, I think that I made a mistake. This should be, no, never mind. That looks right. Well, now I'm confused. Hold on. Did I mess up? So when we have this, yeah, this is messed up. This should be 8 down here, because we are going to take half of the angle. Yeah. So then when we do 1/12 of a circle, we should get pi over 6, yeah, and then pi over 12 times r squared. And so the pattern that I hope you're seeing is that to calculate the area of a sector, we're actually going to take, well, this is how we usually write the equation. I think the pattern that we notice from here is probably more like we're going to take 1/2 of the angle and multiply that by the radius squared. But this is how it's often written as a formula that people memorize. Okay, so as just a reminder again, we are going to use the area of a sector of a circle to build up a new integral. So we're going to do integration in polar coordinates, and this is going to be our fundamental shape, this is going to be our fundamental formula, not a rectangle. Okay, so with that, let's go back to our picture. So this sector of a circle is like our new, it's a polar rectangle. Actually, some people do call it that, a polar rectangle. And so we're going to find the area of that region using kind of the measurements from our polar function. So we'll say that the change in angle here we'll call delta theta. That's the angle that's swept out there. And then this radius is going to be given by our function. We'll call it r sub I. And so with those quantities, we are going to have an area, and again, I put a sub I here to denote that this is like an approximating shape. So the area of one approximating shape is going to be 1/2 r sub I squared, and then times delta theta. And so delta theta is going to function in the same way that delta x did when we were doing this with rectangles. So what we're going to do is take the limit as delta theta goes to 0, so those sectors get, the angle change gets smaller and smaller, and what we get then is an integral where delta theta becomes d theta, and what we're integrating is 1/2 r squared. Okay? So again, the analogy here is that when we did regular old integrals, we went from a to b, and we did basically height, right? This was height times width, because we were looking at rectangles as our fundamental shape. So now what we're doing is we're doing circle sectors. So we're going to have delta theta, which is kind of like a width, and 1/2 r squared, where we can kind of think of r like a height. It's going to be given by our function in any case. So one of the tricky things, really the only tricky thing about setting up polar integrals, is that you have to find these angles, right? So alpha and beta are now going to represent angles in polar coordinates, and that's not always as easy to figure out as the bounds on x are going to be. Okay, so this is the formula we're going to use. Let's look at an example, and again, the main thing we're going to think about is how do we figure out the starting and ending angle for the shaded region we're interested in. So go back to 1 + 2 cos theta, and I would like you again now to pause the video and give this one a try. So as I mentioned, the difficult thing is going to be figuring out what angles sweep out this region of the graph, right? So what values of theta are going to do that? So really the best way to do this, and you don't have to do this by hand, actually that's not going to be a good one. We're going to need it to be a little more like this. There we go. Is like we did in the last video, use the rectangular graph as a reference to try to help us figure out what's going on over here. And you can do this in Desmos. You know, if you wanted to do this in Desmos, you would just plot it as a function y as a function of x. So you can do it as this, and you'll get the same information. I'll go through just generating this graph by hand here because it'll be a little bit faster. So since we just have theta in here, the period is still going to be 2 pi for cosine. And then I always like to break this up in half a couple times because these are the kind of key points for both sine and cosine. This is going to be pi, and this is going to be, well, this one will be halfway, so this will be 3 pi over 2, and this will be pi over 2. So we'll remember that as we go. What other things do we notice here? The amplitude is going to be 2, and we're adding 1 to this, so that's going to shift the whole graph up by 1. So what I'm going to do is I'm going to put a little dashed line here at 1, because that's like the new midline for the cosine graph. And then it's going to go up to 3 and down to -1. So this graph is clearly not to scale. Thank you for your understanding. So the cosine graph, when the angle is 0, cosine is 1, and so that's going to give us a value of 3 when the angle is 0, and that corresponds in the picture to this point over here. And then what happens is cosine will go down to 0 by the time we get to pi over 2. So at pi over 2, we will be at the midline, and then at pi, we will be back at cosine will spit out a -1. So that means that, hold on, sorry. Yeah, cosine of pi will spit out a -1, oh, which actually equals -1, because we're going to have -2 plus 1. Right. So we have that. And then we're back up here by 3 pi over 2, and then we're back up at 3 by the time we get to 2 pi. So if we draw that like we know a cosine curve looks, it's going to look something like that. Okay, so again, the goal is to figure out where is this shaded region corresponding to, because we want to try and find these angles. And so if we follow this graph, right, if we kind of follow this down and think about what's happening on the polar graph, the radius is going to start at 3, and it's going to go less and less and less as we sweep this out until we get to 0. And so that happens to be this point right here, which I didn't mark because I don't know off the top of my head what this is going to be. But it turns out that then the radius will be negative. So even though we're traversing this angle, right, as we think the values of theta are over here, the radius is negative. So we're actually going to be drawing it over here. And that's actually going to be true until somewhere around here. So what we're gonna do is start here, right? We're gonna trace this out, and then because the radius is negative, we're actually gonna trace this out. So that's gonna correspond to the region that's shaded in this picture, or the bounds between where the graph is negative, it turns out. That's not always the case, but in this particular case it is. So what we need to know is, what are these points, right? When does 1 plus 2 cosine theta hit 0? So let's actually just set that up. We want to know when the radius is 0 because we inspected the rectangular graph. So solving this, we get cosine of theta should equal -1/2. So you can check that on a calculator or Desmos, or you can use your knowledge of the unit circle, which I'm sure is quite extensive and impressive. So -1/2 is over here, and sorry, that's not to scale. -1/2 on this scale is actually like right here. So let's see, so cosine is going to be at a half, at -1/2 is going to be at 2 pi over 3, right? So that's, sorry, where's 2 pi over 3? So we're going to go, here's pi over 6, and here's pi over 3, and let's see, so then we go, it should be right here. Okay, so then there's going to be another one down here, and that turns out to be 4 pi over 3, right? We go 2 pi over 3, I'm sorry, 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. Okay, so these are the two values that we were interested in. And so what that means is we've now found our alpha and our beta values. So we can set up the integral. So what that gives us is this area of the shaded region is going to go from 2 pi over 3 up to 4 pi over 3, and we're going to integrate 1/2 times the radius, 1 plus 2 cos theta, quantity squared, and then we also have the, remember to multiply by the d theta in this case, just like we always have to have the dx. Now, I'm not going to ask you to work out these integrals by hand. There are some slick tricks for working out trig integrals, but I don't think they're worth learning. It's fine to be able to set this up and be confident in the integral, and then to take this and plug it into some computational system like Desmos or Wolfram or something. Okay, so I took the liberty of working that out, and you get pi minus 3 root 3 over 2. Turns out to be the area we were interested in. All right, so let's do one more. Again, I'd like you now to pause the video and try to take a couple of minutes and set up the integral that will calculate the area of the shaded region in this case. Okay, so one difference here is that now we actually have the area between two curves that we're interested in. So what we want to find in this case is the point of intersection where the two curves will hit each other, because that's going to determine the end. And again, I just want to draw our attention to the fact that when we think about area in polar coordinates, you really got to shift your thinking, because it doesn't have anything to do with the x-axis anymore. We're thinking of, I always like try to draw a line out here, right? I'm actually going to change colors because the screen isn't showing up so well. So we draw a line from the origin out to the curve, and think about how to describe the area from that perspective, from the curve down to the origin, right? So really the curve is going to go from the outer function, which in this case is cosine of 2 theta, and it's going to go to the origin. But then what we're going to have to do is we're going to have to take away, so maybe from is not the right phrasing here. We can kind of think of, there's an outer function, which is cosine of 2 theta, and there's an inner function that we're going to have to subtract, which is going to be the constant radius 1/2 that generates that red circle. Okay, and so what we're going to do is we're going to find the area under cosine, and then subtract the area under 1/2 in order to, over the appropriate range. So what we want to do is, again, let's take a look at this. What we're going to do is find the angle where this happens, right, where these two graphs intersect. And it sure looks like it's going to be pi over 6. But, you know, it's hard to tell exactly on the scale, so we'll just look at how to do this algebraically. But that's what we want to try to find. Okay, so what we want to try to find algebraically, again, is where these two curves intersect, or where, at which angle they will have equal radii. So the way I think about this is, again, it's pretty nice to use the unit circle. You can plug this stuff into your calculator, but it's nice to be able to reason using the unit circle. So the cosine of some angle equals 1/2. When does that happen? In particular, when does that happen in the first quadrant, right? Because we know that's where the picture is taking place. So that's going to be at pi over 3. So what we can do with that is we can say then, well, when does 2 theta equal pi over 3? And so that's going to be when theta is equal to pi over 6. Okay. So there's our angle. So what we're going to do now is we're going to integrate. So we're going to think of this as a difference of two areas. We're going to integrate from 0 to pi over 6, and we're going to take the outer area, which is going to be 1/2 cosine of 2 theta, and then we're going to square that times d theta, and then from that we're going to subtract, again, the same range, the area between the circle and the origin. So we're going to take 1/2 of 1/2, which is the radius of the circle, squared times d theta. and that's the area of the shaded region. Now there's some algebra that you can do. We got a lot of common terms here. In particular, we have two integrals with the same bounds. So we can actually combine those into one integral, but it's the same thing. The integral from 0 to pi over 6 of the difference of those two things. All right, so that concludes this video. In the next video, we'll do a recap. So we'll do kind of a review of polar coordinates. We'll do some graph matching, plotting some points, and looking at a few other functions to try to calculate area. So we'll see you then.